Okay, we'll go ahead and get started. Your exam 2 grades are in zip grade, so you can check those out. We're going to begin module 3, which is now on oxidation states 2 and 3. We're already familiar with the oxygen functional groups, so those are aldehydes and ketones. We're actually going to use those to introduce nitrogen functional groups called imines, enamines. And then we have these other new functional groups, acetals and aminals. So it's not animal, it's aminal. And those are functional group equivalents. So you go from oxidation state 2 to oxidation state 2, but you change the bonding pattern a little bit. And then we'll wrap up this module on carboxylic acid derivatives. So we'll learn a couple new mechanisms within this module, and really this is setting the stage for how we can access more complex organic functional groups. So we'll go ahead and get started with this. Any questions? Seeing none. So just a brief overview of what these functional groups are in terms of the names, physical properties, and then we'll get into the reactivity. So we'll start with aldehydes. So that's the abbreviation. The R1 is just the rest of the molecule, but aldehyde is CHO. And so that's R1. And then you have that carbonyl at the end of the chain. So an aldehyde is defined as the end of the chain because you have an H and then something else bonded to it. They're named by taking the longest chain. You find the alkane name, drop the E, and add al. So methane becomes methanal, or you probably are more familiar with the common name formaldehyde. So a lot of these smaller molecular weight ones have common names. So ethanal is acetaldehyde. But again, you see the CHO here is at the end of the chain in H. I don't know how much more I can say about that, other than visually recognizing the CHO group as the aldehyde. If the aldehyde has a chain bonded to it, you name it, or a ring bonded to it, you name it a little different. Because you can't have an aldehyde within a ring, because then it becomes a ketone. So it's named sort of as the parent functional group. And the word that's used is carbaldehyde. So let me just point out some things about this structure. So in the first one there, cyclopropane carbaldehyde, we're naming the ring and then just shoving the word carbaldehyde at the end. For this module and then module 4, this carbon that I've labeled alpha, that's the carbon right next door to a carbonyl group. That's always called the alpha carbon. So module 4 focuses specifically on the carbon reactivity of that alpha carbon. So it's special in one sense. When we get to that, we'll talk about why. But for the ring-containing compounds, you'll notice that the alpha carbon is di-substituted, and then you have the aldehyde substituent. So in preparation for your final, we're getting to the stage now when you can have higher oxidized compounds. If you have a polyfunctional compound with more than one oxidation state, the question is, how do you name it? And it's named according to the highest oxidation state. So as we see in this, the leftmost example, 3,4-meal pentanoic acid. So let me put the chain length first in red. So 1, 2, 3, 4, 5. That's where the pentane comes from, the pent. And now you have this substituent on carbon 3, which is an aldehyde. Notice it's named a little different when it's on a chain. It's called a 4-meal group. So, because it's one carbon, one is methane, the common name for that is form. So 4-meal means aldehyde. Now the issue is, and I'll write in blue, that's oxidation state 2 and that's 3. So when you have to name these compounds with higher oxidation state, the highest one gets the parent. So that's why it's called pentanoic acid. And then the aldehyde is just a substituent. So we can see that as well. We have 2,4-meal cyclohexane 1-carboxylic acid. And in that case, the ring is the parent because it has the most carbon, so that's the cyclohexane. And then the numbering in terms of the 1 and 2, since the acid is at the higher oxidation state, it's the parent. So that's why it gets the 1 position. And we also have an aromatic ring, so 2,4-meal benzoic acid. So in that one, necessarily the acid is position 1, and the 4-meal group is position 2. So since this is the module on oxidation states 2 and 3, aldehydes, acids, and their derivatives, they always have to be at the terminus of a chain. The ketone carbonyl has to be in the middle somewhere. So that's, any questions? It's kind of boring. It's just naming stuff.
So you have the carboxylic acid and then how do we say the other one? If you have like a longer chain that's branched out, would that one then become, the aldehyde become the parent even though it is the smaller oxidation?
No, the IUPAC like rules for nomenclature are based on oxidation state. So the highest oxidation state will always win. So that has to be, if you have a chain and then branching, that acid would always have to be in the longest chain. You. So let's convert this name here to a structure, and then we'll go ahead and answer the question. So in doing that exercise, 4-bromo, 2,4-meal, 3-hydroxy butanoic acid. So we start with the end. So butanoic acid, that's a 4-carbon chain butane. And then because it's an acid, that group has to be on the end. So there's the butanoic acid part. That means the carbonyl has to be 1, then 2, then 3, then 4. And then we can just read from left to right and plug in the substituents. So carbon 4 has a bromine. Carbon 2 has the 4-meal group, that's the aldehyde. And then carbon 3 is hydroxy. So again, in blue, the oxidation state numbers, this was 3, 2, 1, and 1. So the point of this is, we learned how to name alcohols. And then when it just had the alcohol, that was the highest priority, so it ended in OL. But now when you have multiple functional groups, you really have to apply that algorithm to it. And so, in regards to Autumn's question, the highest oxidation state has to be in the longest chain when you're determining, that butane, pentane, hexane, whatever it is. Any questions? So what are the structural features of the CHO group? Aldehydes really, I think, have a lot of signature data and the different techniques, so that's highlighted in green there, which are really will increase your confidence the most to say, okay, that CHO is in there. So the IR, which we'll see in a minute, has two things, this CSP2H stretch. So that typically falls below 3,000. And then your carbonyl stretch, in the normal sort of 1,700 to 1,750 range. Mass spec, that's in yellow. It's a little harder to determine. That's really for another class when I talk about alpha cleavage and how molecules fragment. Proton NMR is another strong one because the aldehyde proton is really the only one that will occur between 9 and 10 parts per million. In general, it occurs as a singlet. But it doesn't have to because it can couple into that alpha carbon if there's hydrogens attached. And then in the C13 NMR, usually there's an indicative peak between 180 and 200 of your carbonyl carbon that's sp2 hybridized. But you really have to sort of put all of them together to increase your confidence that it is in there. So here is the 4-carbon aldehyde butanal. And as I shade in red here, that signal, that's the CSP2H. So that's the one that sticks out from everything else. So that coupled with the carbonyl stretch in region 3. So that's your CO double bond stretch. So if you have that, and then if you have a proton NMR and you see that signal at 9 to 10, you can say, okay, at least one fragment in there has to belong to that. So how does the CHO group impact the physical properties? So we've seen before that the oxygen of the carbonyl is delta minus, the carbon's delta plus. So that means that carbon is electrophilic and that nucleophiles will add to it. So in terms of that, what we saw prior were hydride additions and then organometallic additions, basically to make alcohols. So we classified those as reductions. So I have this question highlighted in blue here, which is kind of relevant to what we're going to talk about. Formaldehyde itself is a gas. When you buy it, it's typically a solution in water called paraformaldehyde. And what formaldehyde itself tends to do is form these trimers. So three formaldehydes will trimerize into that molecule shown. So that gives us a sneak peek into the reactivity of aldehydes. So the carbonyl itself can only behave as a hydrogen bond acceptor. So meaning like with water, the lone pair can hydrogen bond with water in that fashion. And so if the carbon count is low enough, the aldehyde can be miscible due to that interaction. But once you get too many carbons on there, like more when you get into like biochem and biology, we'll start talking about lipophilic and lipophobic. So lipo meaning fat. The more carbons you have, the more nonpolar it is. So you have nonpolar and aqueous, they don't mix well together, but if it's a small enough carbon count, that will overcome, that property. So it says compared to the alcohol, the aldehyde will almost always have a lower boiling point. So what that means is, if you're, say, comparing 3-carbon alcohol, so propanol, versus the aldehyde propanal, propanal will boil lower because the alcohol has hydrogen bond donating and accepting properties. So again, when those things interact, you have to overcome the energy of that interaction with more heat, more cowbell. Anyone? No one? Someone got it, okay. And again, in the aldehyde, you're taking away the ability to be a hydrogen bond donor. So ketones are pretty much the same in terms of the physical properties and all that. The nomenclature is different in the sense that you're dropping the E and now you're adding ONE to the end. You can have two types of ketones. They can be symmetric or non-symmetric. So for example, this molecule, propanone or acetone, that's symmetric because both alpha carbons are the same. And if we have this one, this is 2-butanone. Now the groups bonded to the carbonyl are both different, so it's non-symmetric. As we'll learn in Module 4, you're going to put your time and effort into the non-symmetric ketones, because that module is based off the study of the alpha carbon itself. And so the issue is, if you run a reaction with acetone, the alpha carbons are the same, so if the reaction, it doesn't matter where the reaction takes place. But with a non-symmetric one, now you have a choice, alpha versus alpha prime. And so we'll get into the nitty-gritty details of that. How do you select alpha versus alpha prime? And a lot of that gets back to the choice of what base we're going to use to affect a reaction. So you can see the carbon counts here, symmetric, non-symmetric, how you name it. For ketones in general, the number in front of the parent name is specifying where the carbonyl is. So you really want to specify that for ketones. Remember, aldehydes you don't need to because it's always at the end. So that when the carbonyl is embedded in a ring, So now you have these cyclic compounds. Remember, the aldehyde cannot be embedded in the ring. It has to be a substituent. So you can have three-membered, 4, 5, and 6. And so you're just sticking the word cyclo in front of it. And then the parent is just the ring size. So 3 carbons is propane, so cyclopropane. Then if it's a ketone, you add the ONE. So what we're going to focus on is using either the aldehyde or ketone carbonyl groups to run further reactions, whether they're forming compounds with nitrogen that make different functional groups, or we conserve the oxidation state to form these acetals or aminals. Your slides probably have that written wrong as like ether or something, so maybe cross that out and write ketone. So whereas the aldehyde had a lot of signatures from the spectroscopic data, the ketones are a little bit murky because ketone IR, for the most part, will look like an ester IR. And so you have to do a little bit more digging to figure out, okay, does the molecular formula have 1 or 2 oxygens in it? Again, if you see a carbon in the 180 to 220 region, you can be confident that it's a carbonyl carbon. So really in 2-butanone, there's your carbonyl stretch. But now again, if you were doing this sort of with just a collection of data, this one, you'd have to do a lot more thinking about, okay, do things work out to form a ketone, or can it be an ester? How do I figure out the number of oxygens? Because between 17 and 1800, that data will look a lot alike. So I guess we'll just use the butanone as our example here. Again, delta minus, delta plus. So the carbonyl is going to undergo an addition somehow. And again, to recap, you've learned additions of hydride and organometallics. Those are strong nucleophiles. The new thing for this module is, what if the nucleophile is not strong? What are those reagents? How are they different? So same sort of hydrogen bonding scenario with water. So that will be an acceptor. Water will be the donor. And again, these lower molecular weight ones will be miscible with water. Again, compared to the same chain of carbons versus, so an alcohol versus the ketone, usually alcohols will boil higher due to the non-covalent interaction. Any questions? No questions? Questions?
You mentioned about what if the nucleophile is not strong and how it is strong. Can you talk about it a bit more?
We're gonna get to that in a couple minutes. I'm gonna list the functional groups that are weak nucleophiles, and then how they do the additions to the carbonyl. Because again, what you've seen before is when hydride or organometallic add, either one of them, they're going to form alcohols. But when you get into the weak nucleophiles, when they add, they form all different functional groups. Since we already covered the preparation of aldehydes and ketones, I'm just giving you the summary slides of those reactions. So to make aldehydes, you'd take the primary alcohol, again, because it's at the terminus of the chain. So for example, if we had the 3-carbon alcohol, and then we applied Des-Martin, Swern, or PCC, again, that's doing just a one-stage oxidation. So the alcohol becomes the aldehyde. Something we learned from Organic 1, say if we had this alkene, we could treat that with ozone gas. And essentially what that's doing is clipping the two sp2 hybridized carbons from the alkene. Each of those then gets an oxygen that's double bonded. So in this case, we would end up with 2 equivalents of the 3-carbon aldehyde. So that's 4 reactions to make an aldehyde. So for ketones, now the starting material is a secondary alcohol. So if we wanted to make that butanone, we would start with 2-butanol. And again, that's a one-stage oxidation. So it's got to be a secondary alcohol to make a ketone. We learned that tertiary alcohols, you can't oxidize them. Now for this ozone reaction, the alkene has to have carbon substituents bonded to the sp2 hybridized carbon. You can't have hydrogen, because hydrogen is going to end up as the aldehyde. So let me erase. So ozone, then the reducing agent, that would get us 2 equivalents of that butanone. So that point I made when we identify the sp2 hybridized carbon, so bonded to that has to be carbon and carbon. So those become your 2 alpha carbons to make the ketone. So really the same for reagent conditions, but the nature of your starting alcohol determines whether it's an aldehyde or ketone you end up with. So now this is the new stuff here. In the prior module, when we learned about hydride addition or organometallic addition, those are strong nucleophiles, meaning that when they add to the carbonyl, the reverse reaction will never happen. And that's based on pKa arguments. So the nucleophiles we learn now, they can add and then come off. So the reactions are now reversible. So to highlight those words here, so there's hydride or organometallic. Those were strong nucleophiles. And they're irreversible. So overall, that was, again, the reduction of that carbon from the carbonyl to the alcohol. And so what is a weak nucleophile? And then what products what are the names of the functional groups that they form? So in this table on the left, or the first column, are the functional group names of weak nucleophiles. So notice the thing about them is they're all neutral. So an alcohol can be any class, primary, secondary, or tertiary. Primary amine, secondary amine, notice there's no tertiary amine on there. A nitrile, a thiol, which is the sulfur variant of an alcohol, and then water. So those are all neutral molecules. And just to show you again, hydride was ionic. Organometallics, where it's a carbon anion, R minus, that's ionic. Those are strong. They add and then that's it. Weak nucleophiles, again, they can add, but then they can also come back off in the reverse direction. So here is the name game based on what you're starting with. So you have your weak nucleophile. If you're adding it to an aldehyde, an alcohol becomes an acetal. An amine becomes an aldimine, or excuse me, a primary amine becomes an aldimine. A secondary amine becomes an enamine. A nitrile becomes a cyanohydrin. Thiol becomes a thioacetal. And then water becomes a hydrate. So what's really different when you start with a ketone? An alcohol forms a ketal. Primary amine forms a ketamine. The last four all form I guess the ketal is different. So that one would be different. But enamine, cyanohydrin, and hydrate are the same. And again, what you want to learn here is the bonding pattern of the functional group that makes up that name. So again, this is the oxidation state should be able to help you with that. So we'll go through these, not necessarily in the order that's listed in that table, but we'll go through most of them to see what they look like, how they're formed. We'll do some mechanisms to push arrows. So when we have water plus an aldehyde or ketone, that forms a hydrate. So again, water and alcohols, they have the same OH functional group. When it's specifically H2O, it's a hydrate. But then when it's an alcohol, it's either an acetal or ketal. Nowadays, most people just call either of them an acetal. So if we use this model compound here, 2,2,2-trichloroacetaldehyde, we can treat that with water either under acidic or basic conditions. It's going to form this product here. And really that carbon is the hydrate. When you look at the difference in molecular formulas between them, like if you took the product minus the starting material molecular formula difference, it's H2O. So that's why it's called the hydrate. So that's called chloral hydrate. You can look up the name of that gentleman there. So on the next slide, I'll show you the conditions under the acidic and basic pathways.
Is it the catalyst that determines what affects the aldehyde or ketone?
The catalyst really is telling you what charge you're allowed to draw on the mechanism. So under acidic conditions, you have to be neutral or positive. Basic conditions, neutral or negative. But you're still ending up with the same thing. So I'll draw the first one under acidic conditions. So we're going to use hydronium. And so hydronium ion is our acid. So the carbonyl oxygen has to be our base, which means it's going to get protonated. So what that serves to do is it makes the carbonyl group more electrophilic. It wants to be attacked more. And I'm drawing these arrows forward and backwards. That means equilibrium. So through equilibrium, you can control, through the principle of microscopic reversibility. If you're at the product, you can take that and revert it back to the starting material based on if you're removing water, adding water, that sort of thing. So if that gets protonated, the carbonyl now has to be plus. And then what I'm going to do for this is just draw a resonance form so you can see why the carbon gets attacked. So a resonance form would push the positive charge onto the carbon. The oxygen would then be neutral. So that's an electrophile, and then water is the nucleophile. So that's going to add. So we're not quite done because that oxygen is plus charged. We just invoke water to act as a base and abstract it. So that will generate the hydrate and then regenerate the acid catalyst. So in terms of writing mechanisms, if something is used as a catalyst, as you push the arrows, you should be able to regenerate it. Show that you're regenerating it so that it can go back into the catalytic cycle. So what I want to point out about this, we're starting at an oxidation state of 2. And then what oxidation state are we ending at? 2. So what's the difference between them?
The functional group?
So you have sigma and pi, and now you have sigma and sigma. So you're conserving that oxidation state, but now you don't have that pi bond. So acetals are resistant to nucleophilic attack. this carbonyl, it's adding, when it gets to this stage, it's adding that water. So that's a nucleophile attacking it. But now when you're at this oxidation state with 2 sigma bonds, nothing can attack that carbon. But based on the mechanism, the acetal is sensitive to going back the other way. So really what you would do is just add a lot of acid to this, sort of heat it up, and then drive it the other way. If you wanted to, maximize the equilibrium, you would just swamp this side with a lot of water, because that's going to consume the starting material and push it that way.
And will this mechanism be fundamentally the same fit ketone instead of an aldehyde as a starting material?
Yeah. So yeah, the question was about, what for a ketone, it's pretty much the same, so I don't have a slide on that. But the important thing to remember is under acidic conditions, you have to protonate the carbonyl first, just to remain sort of positive in the mechanism. So if you're using sodium hydroxide, now you can start showing negative charges. So that oxygen's negative, which means we can invoke a negative oxygen of the carbonyl. So this will add, you don't activate it first, it just adds. And now when that pi bond breaks, that oxygen gets the negative charge. And so we're pretty much almost there. We just have to do a proton transfer from water. And then we've regenerated that catalyst. So the thing with the name here, so the hydrate is, specifically that. And so here we're showing carbon and then H, so that's aldehyde. If that was carbon, the stuff in yellow would still be a hydrate. Any questions?
Still the separate reactions?
Yeah, so the top is the acidic. So the acidic mechanism and then basic mechanisms.
And the basic one will regenerate the base again.
Yes. So this conservation of oxidation state is important for carbonyls. We'll learn more about it in Module 5 with biomolecules, because sugars, carbohydrates, the main functional group in there is of this nature. They're not hydrates, but they're called acetals. And again, the only difference is water forms a hydrate, an alcohol forms an acetal. But you still have these 2 sigma bonds to the oxygens. Still see some writing. I'll give you a couple seconds. I guess what I can say in the meantime is, even though you're forming this functional group, again, what they're used for is because you're conserving the oxidation state, they can be used as a protection step. And we'll see some examples of that in the questions a little bit later on in 10 to 15 minutes. So now getting away from water, if you have an alcohol. And so the example I'm going to use is methanol, but really it can be any alcohol. So this part here, what I've highlighted in green, that can be anything bonded to that OH group. The mechanism is going to be the same. So we said that we have that oxidation state 2, and we're conserving it. So really, when you look at that that acetal, you see the 2 sigma bonds. You should know or be able to realize that since that's oxidation state 2, that's carbon, that's hydrogen, it has to come from an aldehyde. Then the other thing to realize is the stuff bonded to those oxygens, it's 1 carbon. So that has to come from methanol. So just pay attention to what the structure is telling you about, the product. And as I stated here, acetals do not undergo hydride addition. So we can reduce that carbonyl with hydride or organometallic down to an alcohol. But if we form this and then we treat that with like lithium aluminum hydride or some Grignard reagent, it's not going to reduce that carbon. It cannot react there. But again, if we wanted to take the product and unmask it back to the aldehyde, you just reverse the conditions. So in that case, you would take basically your acetal, a little bit of acid, and a lot of water would convert it back this way. So we'll draw the mechanism for this one. I think I'm just going to draw it under acidic. So 4 carbons and conditions. And methanol. So our acid catalyst, the first job is to protonate the carbonyl. And again, the purpose of that is to make the carbonyl more electrophilic so that the alcohol can attack it. So again, you're essentially running the reaction in methanol. It's the solvent and the nucleophile. So notice when I do that, I'm not generating any negative charges. And we'll just have water do the proton shuffle. So once we do that, that helps us regenerate the hydronium. So you see now, we still conserve the oxidation state, but we have OH and then OCH3. So when you have something that's mixed like that, the word hemi is given to it. So that's called a hemiacetal. And then what do you think the next step would be? Because we got to get rid of that OH. Sprinkle some pixie dust on there, magic happens. Again, because we're under acidic conditions, we have to protonate now that other OH because we want it to leave as something neutral. So this will be a base. We'll have our hydronium as the acid. So we're going to protonate that. And that plus charge just migrates over. So now the reason for doing that is in this next step, that other oxygen is going to do an elimination. So it's going to come down and push out water. And so this is just like before, where I'll show you a resonance form where we just move the plus charge onto the carbon. The oxygen's then neutral. Our second molecule of methanol comes along to attack it. And then since we spit out water in the other step, we'll just use that as our base, and that will regenerate the hydronium. And that's an acetal. So again, acetals are important because carbohydrates like sugar or glucose, ribose in DNA, they have that functional group in there. That allows them to form other compounds at that acetal center. So depending on what's bonded to that, you get these different carbohydrates, those biomolecules, they serve different functions in living organisms. Yep.
Just to make sure this is the same thing for the ketone.
Yes. So I guess that brings up a good point. So aldehyde begins with A. So in an acetal, so there's your oxidation state 2. You have carbon and H. In a ketone, it's called a ketal, so it's carbon and carbon. But I don't know, I call everything an acetal, just for whatever, but really once you identify that carbon and you look at what's next to it, you can tell whether it came from an aldehyde or a ketone. Yep.
How do you understand that transition to the carbon, right?
This one.
This one to the rounding.
So this oxygen's neutral. It has the two lone pairs. What it's going to do is push one of them down to form a double bond. And through that elimination, water can leave. So water's a nice, stable, neutral compound. It's a good leaving group. And then it forms this. This resonance form shows that the plus charge on carbon. This is on oxygen. This is called an oxocarbenium ion.
That one?
The whole thing together. Any other questions? So one other example of this that's pretty important. So ethyl has the form SH. So it's like an alcohol, but the oxygen is now sulfur. What's interesting about this is from the prior example, we had two equivalents of methanol. You can actually tether the alcohols together into one molecule. So in this case, we're using a dithiol. These could be oxygens, but I'm just showing you the sulfur version. And they're tied together by this linker. So one molecule, and then there's your two equivalents. It'll go through the same mechanism where that oxidation state 2 is conserved. Now you have sigma bond to sulfur and sigma bond to sulfur. And so that's called a thioacetal. Sulfur is a bit unique in the reason that you're learning this. You can take this compound at oxidation state 2 and then fully reduce it down to the alkane. You cannot do that with the oxygen version. So the analogous oxygen version would be this. So you've made the thioacetal. Then with hydrogen gas and a special form of nickel metal, you can reduce that all the way down to the alkane at oxidation state 0. So again, the reason that's useful is because you can take advantage of the oxidation state, protect it, do some chemistry, and just get completely rid of it. We'll have a couple examples where we see, how we can use that as a strategy. So to summarize, what we've learned, carbonyls undergo addition with strong nucleophiles in a reduction process. When you use the weak nucleophiles, you conserve that oxidation state. Those products, the hydrates, acetals, ketols, they're stable to nucleophilic addition. You can then reverse the reaction and take those two sigma bonds back to the starting carbonyl. So really the take-home message about this is when you're thinking about long sequences of reactions, sometimes you have functional groups that are incompatible with one another. So you have to protect something so you can do a reaction somewhere else and then deprotect your original site. So here's an example of that. We have this molecule ethyl 3-oxobutanoate. Let me just put in the oxidation state 3, 2, 2, and 1. So we want to take that and make 4-hydroxy butane 2-one. So here in blue, notice that oxidation state's conserved and the other one's reduced. So remember the issue with carboxylic acids and esters. So only lithium aluminum hydride will reduce that. But lithium aluminum hydride reduces everything. So if you just take this and treat it with lithium aluminum hydride, you end up with that product. So now you've reduced them both. But then you could say, well, I'll just go oxidize the secondary alcohol. Then the question is, well, you can't do that because you have a primary alcohol. You're just going to oxidize both of them. So how do you get around this issue of functional group compatibility? So the strategy here is you have to do multiple steps to sequence protecting the ketone, reducing the ester, and then deprotecting the acetal. So in terms of the steps, and then I'll write the individual products after. Step 1, we want to protect. So we could use, let's say, conditions E. That's going to protect that. Notice we conserve the oxidation state. Now that is stable to any sort of attack. Now in step 2, we can do what we want, which would be conditions B, lithium aluminum hydride, and THF. That's going to do our reduction. And now in the last step 3, we can treat with conditions D, so we'll unmask that acetal back to the carbonyl group. So really what we're designing this around, we want to do the reduction, but then we have to add these 2 other steps, the protection and then the deprotection of the ketone.
Do the last step because it's an irreversible reaction.
Say it again.
You could do the last step 3 and make it back to a ketone because it's a reversible reaction.
Yeah, so because now we're using like a lot of water in there,
That makes sense.
it's basically gonna, the mechanism that we drew to make this acetal, you're just sort of starting there and going back the other way. So for example, that oxygen gets protonated, and then this oxygen will push that out so water can attack it. You end up with the hemiacetal, and you just sort of keep going back till you get to the ketone. So a lot of these reactions are really just proton transfer for the most part, under the requirement of the acidic or basic condition so you get your charges right. So what if we want to take this, these next two problems are the same in terms of the overall transfer, but just sort of two different ways of doing it. We want to take 3-pentanone all the way down to pentane. So from what we just learned, we would first make the thio ketal that has the sulfurs in it. And then since, again, that's special, we can just use the rainy nickel to reduce it all the way down to 0. So step 1 would be conditions J. So that uses the methane thiol. And that acid that's shown, that's a Lewis acid. It just behaves the same way as the Bronsted acid. The carbonyl, it gets activated by the boron, then the sulfur attacks. You do all this stuff, and then you get both sulfurs on there. So that's the thioketal. Now the hydrogen gas with the rainy nickel will completely reduce that. So that's C. So H2 gas, rainy nickel and methanol. We get pentane or a very wide W. So that's one way of fully reducing an oxidation state. So the next slide is the same transformation, but can you think of another way of doing it that's not this? Based on the reactions that we've learned so far this semester. I think the transformation conditions, yeah, the conditions are the same. Anybody got a sequence of letters they want to shout out? It's like that, name that tune. I can do this in 4 reactions. So the way we'll do it is connecting into the last module, like all the stuff we've learned there. So we know that we can reduce a ketone to an alcohol, so we're going to do that. But OH is a really bad leaving group, so we have to do some other stuff first, and then really just get that oxidation state all the way down until it's a hydrogen. So we'll do step 1 with conditions A, that's sodium borohydride in methanol. So that brings it down to oxidation state 1. And now we have to spend just time futzing around with it so that we can get another hydrogen in there. So you can't treat with a second equivalent of H minus because OH is not a good leaving group. So what we'll do, since we have an alcohol, let's take H. So PBr3 and THF. That takes the alcohol to a bromide. So this bond is delta minus, delta plus. We need to reverse the polarity. And to do that, we'll make a Grignard reagent with magnesium, so conditions K and THF. So now essentially we have a carbon anion. So magnesium plus, carbon minus, and at that point we can just quench with acid, which would be conditions E. And then we've fully reduced that carbon. So the next one, maybe I'll let you practice, see if you can figure it out. Then we're going to learn how to make cyanohydrins, so addition of a carbon nucleophile that's negative, but it's a weak nucleophile, so it's not a strong organometallic. Those make cyanohydrins, and then on Monday we'll learn about forming imines and enamines from nitrogen nucleophiles and everything we can do with those.